Creating diverse character animation is bottlenecked by the need for large, style-specific datasets. To address this, we present STyMo, a fast, controllable, few-shot style transfer method that learns from just seconds of paired motion. Our model trains in under 2 minutes and generalizes to arbitrary new content, effectively solving the production bottleneck of authoring stylized datasets. Current approaches struggle in a few-shot setting. Example-based methods like GME often fail on complex dynamics. Generative models like Ganimator and SynMDM require the input content to match the training data. Meanwhile, pre-trained models, like most, fail to generalize to novel styles and input content outside their training set and require hours of stylized data, which does not solve the current bottleneck of style motion authoring. We train our system on paired motion sequences, a neutral source, and a stylized target. This input can be very short, often just a single walk cycle or about 2 seconds of data. Instead of learning the absolute motion, STyMo focuses on these style deltas. We calculate the difference required to transform the neutral source into the stylized target. During training, the model learns to predict style deltas based on the source motion kinematic features. Once trained, this lightweight model can be applied to arbitrary neutral sequences of any length. We simply predict the style deltas and add them back to the source to generate the final result. However, to make this controllable and robust, STyMo is actually composed of 3 main components: a static model for time-invariant posture, a temporal model for frame-wise dynamics, and a gating model that ensures style is not applied to far out-of-distribution poses. This decomposition enables independent control. We can scale the static deltas to adjust posture intensity without affecting speed, like the spine curvature in this sad style. Conversely, scaling temporal deltas exaggerates dynamics, like the intensity of a punch. The temporal model is critical for capturing subtle movement. Using the static model alone results in stiff animation. The temporal component recovers essential details, such as the exaggerated arm swing of the sad style, and also the cyclic heavy breathing motion. Lastly, the gating mechanism ensures robustness. Without it, extreme, out-of-distribution poses like crawling produce severe artifacts. The gate detects these contexts and suppresses the style to maintain a valid motion. By processing only previous predictions, the encoder acts as a phase manifold. This independence from the source allows it to generate acyclic, one-shot actions like this punch. Since these actions happen probabilistically, users can also explicitly induce them by injecting training motion into the encoder's input. This allows us to trigger specific gestures on command, for example, increasing the punching frequency. Through cross-attention, the decoder gates these actions based on context. For example, while the encoder may suggest a punch, the decoder suppresses it when the character is sitting, ensuring the style respects the source motion state. With training taking just a couple of minutes, the workflow is fully iterative. If a model trained on walking fails to generalize to running, the artist simply adds a running clip and retrains to fix it. Artists can also refine specific contexts using static poses. By manually authoring just one paired target pose, the static model updates to correctly stylize the character whenever they crouch. STyMo robustly generalizes across datasets. A style learned from the public Mocha dataset is successfully transferred to another motion dataset, effectively handling different actors. It also handles extremely short input sequences, stylizing loopable game animations, even sequences as short as 18 frames. First, we compare with our baseline, an example-based method. While it works on simple data, it fails on motion-captured styles with continuously varying deltas. In this robot style example, it produces an incorrect result, whereas our method correctly learns both the characteristic posture and the slower walking pace. Generative methods like Ganimator and SynMDM struggle when the input content differs from the training data. When applying an angry walk style to a jump, SynMDM ignores the input entirely and simply replays the training walk. Ganimator preserves the jump but reverts to a neutral style. STyMo preserves the content while correctly synthesizing the style, including actions like punching. Finally, pre-trained models like most fail to generalize to novel styles outside their training distribution. Even for a common label like sad, most produces a generic output that misses specific details like this spine curvature. It also generates incorrect locomotion on out-of-distribution inputs, whereas our method generalizes robustly regardless of the content. Thank you for watching.